By now you've learned the basics of heat transfer. You have learned when it happens, why it happens, and where it happens. Probably you've also been given everyday examples of it. A house in the cold, a pot on the stove, or a radioactive sphere that someone decided to drop in the ocean just to make poor engineering students do the math.
And that's great, but if you're actually working in the industry, those aren't the kind of situations you'll be presented with. You'll be dealing with specially designed machines that have been specifically engineered for the situation that you're in. Now, these machines can come in a variety of shapes and sizes, but they're all called the same thing. These heat exchanging structures have been given a name that could only be developed by the combined artistic and creative genius of the entire engineering industry. That's right, heat exchangers. It was a real stretch for that one.
There are a few different types of heat exchangers, each with their own benefits and detriments. But before we get into differentiating them, there are a few common operating principles that we need to understand.
There are a couple governing equations to keep in mind. The first is Q equals mCp delta T. This expression relates the energy a material receives to the temperature it changes in response. The mass of the fluid in question and the specific heat capacity of the material itself determine how much the temperature will change for the same input of energy. It's simple. If you've got more of something, it's harder to heat it all up. And if the material itself reacts less to energy, the same is true. In this case, we need the equation to determine how much energy a fluid needs to gain or lose to achieve the temperature that we want.
The other equation to hold on to is Q equals UA delta T. In this case, we're talking about the driving force of energy transfer between the fluids. How much energy you can move from one fluid to the other is mathematically bound by the overall heat transfer coefficient, the area of the interface, and the temperature difference from one fluid to the other at a given point in the system.
These equations give us an idea of what properties we can change to get the most out of our system. Whatever we can change we refer to as control parameters.
We can break control parameters into a couple of groups. The first are design parameters. Again, fantastic naming by the engineering community. Most simply, these are the variables accounted for by how the system is built, or how it's designed. How about the overall heat transfer coefficient? Well, since that's a question of what material we use, be it wood or steel or copper, well, if you're using wood, you might be insane, but you're in engineering, so we already knew that. How about another property? What about the area of the interface? Well, if you just pick a shape, you can just go on from there and size your system appropriately. Again, that's going to be a design parameter. The other kind is an operational parameter. The first property that fits in this category is the mass flow rate. How much fluid are you pushing through? You might be working with a lot of liquid, or maybe just a little. Another thing we might consider as an operational parameter is the temperature for the system. What temperature is the fluid entering at? It can be cold, it might be hot. These are things that an engineer may have to adjust on site. Both of these are not traits of how the system is physically designed, but how the engineer is using it. These are operational parameters. Another property that we can design for is the type of flow going through a system. We'll get to types of system in a second, but here are two simple illustrative options. You can have the fluids going in the same direction, as seen above, or in opposite directions, as you see below. The first case is called parallel or co-current flow, and the second is called countercurrent flow. Luckily, we have ourselves some prime examples of what you may see in the field. We'll be dealing with the concentric tube heat exchanger and the shell and tube heat exchanger. The former is much more simple, and the latter is much more common. First, we'll start with the most basic heat exchanger design, a concentric heat exchanger. It's incredibly simple. One fluid passes through a central pipe, and another passes through an annular space between that and a larger pipe. This is a design that's quick to set up and easy to size.
These are extremely simple to design and to install, as well as to repair and maintain, but they are very inefficient. They pay for the price of their simplicity by basically losing up to 80% of the efficiency that you can have.
Another type of heat exchanger is the shell and tube heat exchanger. In these heat exchangers, there are a lot of small tubes that are inside one large shell. Fluid passes through the smaller tubes in one direction and the large shell in another. But to prevent regions of stagnant fluid inside the shell, there are blocks called baffles that force the fluid to move in a pattern.
Shell and tube heat exchangers can come in a variety of shapes and sizes. You can do a lot of things to change how it works. You can make the fluid move back and forth in a lot of passes. You can add in a lot of different tubes. And you can change the actual sizing of the system itself. Now, the more complex that you make a shell and tube heat exchanger, the more efficient you can usually make it. However, it becomes a lot more difficult to repair and maintain. That is the price of the efficiency, is exactly how complex you make it. These are by no means the only types of heat exchangers that you'll see in the field. There are a lot of different kinds. There are fin heat exchangers, wheel heat exchangers, regenerative heat exchangers, any number that have been designed for different purposes.
The two presented in this video are important for both understanding the underlying principles of heat exchangers and to see a couple examples of common types. You might not have a choice about which type of heat exchanger you're using in industry, but as long as you keep in mind the basics, you'll be fine. But as long as you keep the basics in mind, you'll be fine. But as long as you keep the basics in mind, you'll be fine. But as long as you keep the basics in mind, you'll be fine. But as long as you keep the basics in mind, you'll be fine. Fine, no!